All right, everybody, welcome back into the room and thank you very much. My name is Moriba. I will be your host and moderator for this exciting panel. It's called AI for Space, but really think about it as, how can we elicit the help of machines to make human lives better and help in the decision-making processes, and even be able to use this in a way to better understand and monitor our activities, especially things that we're doing in space. So with that, I'd like for our panelists to just briefly introduce themselves, and then we're going to get Benjamin to be the first person to talk. So,
all right, that's not working.
Yeah.
Benjamin Fuege-Miller. I'm a Ph.D. candidate under Dr. Moriba here. Also do some work with the applied research labs we have out at the Optical Research Center.
Sure. I'm Thomas Gonzalez-Roberts. I'm here visiting from the MIT Astrodynamics Space Robotics and Controls Laboratory. I'm a PhD candidate in the Department of Aeronautics and Astronautics.
Hi, I'm Solera. I'm also at MIT in ARC Lab. I'm an MS candidate. In case you were wondering, this is my service dog. His name is Baz. He's used to people ignoring him, so he's not sure why you guys are looking at him. If he gets a little excited, I apologize, but we'll be good.
I'm so happy that you introduced me. So with that said, and I think hopefully we'll be hearing about AI from Baz.
Yeah, he's picked up a lot.
Okay, awesome. Booyah, that's some chat GPT. All right, man, do your thing.
All right, so I'm with the Oden Institute, and our work here is kind of focused on how we can make detections from optical telescope data. And all right, sorry about that. How we can go about making detections from the optical telescope data we're provided, and try to go into meaningful measurement data that we can use for determination processes and so on. And we're investigating more novel techniques that can be applied in sort of a generalized framework, whether they're provided by the amateur astronomy community, so you can try to get additional increased number of measurements available to us and try to increase our confidences for purposes that have been clear throughout the past day and a half of the conference. If we're working in cislunar environments where situations can rapidly evolve, or there maybe more are there interesting non-traditional techniques we can consider that might be useful to the problem. So I'm going to skip through some of this. One of the main challenges with optical data is that there's a huge variety of noise that we have to deal with when we have any kind of optical data system. There's motions from the telescope mounts, the relative dynamics of the orbital objects, the noise contributions from the particular optical and sensor subsystems. And traditional detection techniques have required us to develop high-fidelity models of all the various noise contributions within some kind of data, remove them out to try to allow us to just detect those features of interest that correspond to actual orbital objects. In a machine learning environment, we're talking about convolutional neural networks and so on. We are trying to train data sets, or train the algorithms on data sets of just a large body of data. We're talking about terabytes and terabytes of video information. But the objects of interest for us are only a few pixels wide, very sparsely distributed. And trying to train a kind of system on this kind of information can introduce some real world fragility. And if we're dealing with situations where data can be highly variable, say all the different kind of data can be provided by an amateur astronomy community, or an on-orbit sensor suddenly deteriorates, are there any kind of generalized methods which can be applied that can have more robustness? And we are not so much interested in low SNR performance of these methods. We already have machine learning algorithms which are really good at low SNR detections. What we're interested in here in developing these non-traditional techniques are in more generalized methods, so we can process large volumes of data to try to make these additional detections that can improve our confidences for a good space situational awareness. And the methods that we're introducing here are going to be based in multiple hypothesis testing rather than traditional sort of noise modeling machine learning methods. So we're going to try to make hypotheses about how the data is going to behave, develop some test statistic with which we can measure the data, and probabilistically try to pull out what objects are likely to be space objects. Now, these hypotheses are used in traditional methods by usually, removing all the noise sources so that we have some really high fidelity model of what the noise about what the actual background data is. And if you know what the noise is perfectly, well, this isn't really a problem. But in our situations, we don't have these noise models available to us. So how do we go about making hypotheses? Well, according to sort of more psychological and physiological theories about humans perceive vision, there's some theories that we don't actually look for, or a human eye doesn't make very complex noise models. Rather, what we perceive are features which are really unlikely to be attributable to very simple noise statistics. And in sort of a building block fashion, we figure out by process elimination, these features are not attributable noise. And among this family of features that are not attributable noise, a further subset are even more interesting, and so on. So more of a sort of iterative way of learning from information using very simple assumptions. We are not making, we're not so interested in what is the noise model as in what is the consequence of the noise model. We're not interested in, say, the shape of all stars. We don't need to know exactly the point spread functions. We just need to know that these features are a result of some noise process. And this allows us to make very minimal assumptions about the data. For metadata purposes, we only really need to know the time of data collection and observed position so that we can perform astrometric calibration. So we can go from pixels to bright ascension declination coordinates. And with regards to the actual object features, all we have to know is that our telescope is run in such a way that we can sort of put a bounding box around any feature of interest. And indeed, we look over all possible regions of the data. We don't care about the scale orientation, shape of features. We're trying to look for any kind of feature which cannot be attributable to noise sources. And then from this family, try to look for common underlying patterns which could be attributable to noise, project these, and by process of elimination, look at detections of potential and perpetuating space objects. We do know cautiously that this method is very simplistic, and so its precision, its raw precision is not very good. It is really great at being able to tell you roughly where an actual object is in some kind of optical data with high type 1 or false alarm projection. This does require some post-processing procedures using information we've learned from these processes about where an object is sort of roughly locally located and what kind of point spread function it approximately is, and using these trying to do sort of refine detections and get out the exact subpixel accuracy you need for determination. But unlike traditional processing techniques, you now have a lot more information available to you after performing these inference processes. And I want to show you some videos real quick. We've applied this methodology to some data we've collected that we presented in earlier feature work from telescopes we operate out of Mexico, as well as real-world data collected for astronomy purposes provided to us by our Sky and Celestron. So in the first case, come on. Oh no. All right, well.
Might not.
Thankfully, I still have plots here of the right ascension declination tracks we were able to extract.
No.
The videos we are playing, I can provide to any interested party later on. At least we have the image of what we're kind of looking at. If you look at this entire image here, that is one frame kind of scaled down of some data from our New Mexico telescope. And then where that rough blue dot is in the upper right-hand corner in the very center are an actively tracked object and an untracked object that serendipitously passed through the frame. Now, we're not making any we're not removing any dark bias frames in this image. We are trying to learn that some object is moving through the frame in a way that does not hold with the rest of the kind of noise behaviors that are in the data, all the hot pixels which remain stationary, all the stars which are going at a certain angle. And we're able to detect the right ascension declination coordinates and up there of some real GPS satellite. I believe the it's a GPS calibration object. and we're able to detect it and some other object that is serendipitously passing through the frame, and these were about an SNR of 15 and SNR of 3. From our external collaborators, we were provided data of much wider field of view data, 5 degrees by 7 degrees. And we're still able to make meaningful right essential inclination measurements, even though we were provided any additional calibration information from them other than just the a raw fits image without any kind of interesting metadata for where it's pointing or what it's looking at. And we were able to make sections down to SNR 5. Notably, we did detect multiple other objects that passed through the frame, but these were not converted into actual time series information, as they did not last through enough frames for meaningful orbit determination. You need at least 3 measurements over time to build a perform an initial orbit determination process. Or our track association steps were a bit fuzzy, but those points were not based on the multiple hypothesis testing procedures that we were testing and our point for future work. Finally, we provided additionally observations of geobelt objects, so much more distant objects than we were used to seeing, as we were used to looking at GPS data in medium Earth orbit. And critically, we provided data from an urban observer, someone within just a suburb, collected data with a backyard telescope, and we were still able to make true positive detections without any false positives of likely geobelt objects. This was pointed at I believe, a certain object, Galaxy 15, I believe. We didn't detect that specific object because its SNR was below 2. We found our processes we're using for initial segmentation approximately broke down, but we were able to detect actual objects that you can visually confirm in the data. So with that, we believe that these kind of inference processes are maybe applied in a more generalized method. And so they can be more broadly applicable in situations where you have highly variable noise content, where you might not be able to have sufficient training information to run some other kind of machine learning algorithm. And it allows you to make a lot of detections from a huge body of data while minimizing the type 1 error, which we believe is going to be very important if you're chugging through just terabytes and terabytes of visual information. With that, I think we can go on to the next speaker.
Thank you. My paper and Liz's paper, which are available online, and we encourage you to check them out, are a pair. They're sisters. And they together tackle one example of where we find that machine learning can play a helpful role in space situational awareness. And I'm excited to be on this panel because I think there are plenty of opportunities where it can be helpful, but I also hope we get a chance to talk about places in which it might not be that helpful. My time in graduate school has perfectly corresponded with this frenzy of applying machine learning techniques to every corner of every field in applied engineering. And I'm happy to be a part of it because there are opportunities in which machine learning, particularly pattern detection, is particularly helpful for space situational awareness. And so one opportunity that we found in our work together is in geosatellite behavior. We know a lot about geosatellite behavior because we can speak about it off the cuff. We're familiar with why satellites are in geo and the patterns with which they follow an operational lifetime. And performing station-keeping maneuvers in both the north-south and east-west directions. Those are Earth-centered, Earth-fixed directions that only really make sense in geospace, but we're lucky that they do. It makes the problem de-dimensionalized and quite easy to understand. So instead of being in the 6 degrees of freedom of traditional Cartesian orbital elements, we can speak in just 3, latitude, longitude, and altitude, geographic coordinates that make sense when objects are relatively fixed in the Earth-centered, Earth-fixed frame. They appear nearly stationary in the sky. And as the geopopulation grows and the number of observations by commercial SSA operators, of which many are in the room, the density of the data is getting richer. And I can see that firsthand just in my time studying these issues for the past few years. And so as that pattern continues, geosatellite operations and satellite behavior in that domain become better and better poised for machine learning techniques. And so one that we decided to focus on in our work together is using a formulation that we call geo patterns of life. And together we formulate ways to characterize a geosatellite's pattern of life. So in the next few minutes, we want to tell you about how we did that and how it can be applied to better understanding the environment in geo specifically.
Thanks, Thomas. So I'm sure most of you, if not all of you, have heard the term pattern of life before, but it's a term that is defined inconsistently. So in this case, when we say a pattern of life, what we mean is a sequence of behavioral modes separated by nodes that are exhibited by an individual satellite. And what we mean by behavioral modes is, for example, you could have a satellite that's station keeping, doing east-west and north-south station keeping. That would be an example of a behavioral mode. You could have a satellite that's only doing east-west station keeping. That's also behavioral mode. You could have a satellite that's doing a longitudinal shift maneuver. That's also behavioral mode. There are many examples. And when we, we want to process a large population of satellites to figure out if there are, any trends that can help us be better about space situational awareness. And so when we are characterizing pattern of life for a large number of satellites, we want to do this efficiently. We want to be able to use an algorithm to do this so that we're not having to look at the data, satellite by satellite for, years and years of this history. So we used an algorithm to detect these nodes to separate out each behavioral mode. We did this by looking at the longitudinal position history of geosatellites and looking for places where the satellites were initiating a drift or adjusting their drift and ending their drift. And those were our 3 types of nodes. So if you look at a longitude history for a satellite over many years, it's very easy to see when that satellite changes station. We took this for the purposes of our paper. We decided to say that a station, like when a satellite is station keeping, that's within half of a longitudinal degree. And so we looked at the standard deviation of the longitude over periods of 24 hours. And we stepped through all of the histories to get that signal of the standard deviation. And you're actually able to see very clearly where these nodes occur. And it's extremely simple and very fast to detect those. You don't need anything complicated. You just, you can set a single threshold for, this is the value that I want to set my detection at, and anything above that is considered a node detection. And that works for the majority of cases. We ran this test on a diverse group of satellites with different missions, different operators, different buses, different ages, and across the whole board, the simple algorithm, it detected upwards of, it was 85% of all of the nodes that we were able to identify visually. And in histories that are very node dense, this number was well above 90%. So this, even with a very basic algorithm, this is a system that works very well if you're trying to process a lot of satellites all at once to kind of break up this pattern of life and determine, which segments you want to study. And I will let Thomas talk a little bit more about the behavioral modes and what we can do to process those.
Thanks. So with Liz's work, we have an idea of where these nodes are when a satellite in geo changes its behavioral mode. And in my paper, we better analyze what those behavioral modes actually are. And so there are places where machine learning does things better than me, and there are places where I do things better than a machine learning algorithm. So a machine learning algorithm does not get tired with time looking at data over and over again. It doesn't need snack breaks like me. It can look at millions of lines of data and continue churning through it. But it also does not have some of the biases that I have, where I'm familiar with how many satellites in geo perform station keeping maneuvers. I've spoken with geosatellite operators. I've been in the mission control room and seen what sort of protocols are followed. But I'm biased with which rooms I've been in, which operators I've spoken to, and it's not representative of the entire geosatellite community. And so the machine learning algorithm has no idea about these practices, and instead it's just looking at the data. So together we developed a clustering algorithm it's an unsupervised machine learning technique that looks at behavioral modes, little segments of time when we know a satellite is in one behavioral mode. It's doing something, but we're not quite sure what that something might be. It's station keeping, but we're not sure exactly how. It's drifting, but we're not sure if there's any electric propulsion aiding in that drift. And the clustering algorithm finds patterns and finds groups of similar segments to help define these new behavioral modes that have the ability to transcend past the operational behavioral modes that we're familiar with for those of us who've spent some time with geo operators. And if this project were to be continued to other orbital regimes, spend some time with LEO operators. There are some challenges there. Machine learning algorithm doesn't know too much about the space environment, so I can give it little legs up here and there by taking out some bias on the longitudinal space system in general, where I wanted to make sure that the algorithm could identify a longitudinal shift, but not care too much if it were a longitudinal shift over Asia or over Africa with different longitudinal position values. Those magnitudes of the longitudinal position measurement don't particularly matter in terms of what that behavioral mode really is. Where it's happening in the geobelt doesn't matter for how fast that drift was, or the rate of change of that drift, for example. So the paper showed promising results, and we could really use machine learning to get a better idea of these behavioral modes and sort of lean on its capabilities that are better than traditional methods in the space situational awareness analysis community. And so we're particularly excited about a few opportunities to use this analysis. One of them that is important to me, my PhD dissertation is on ITU space sustainability guidelines. And this came up in the conversation surrounding Rich Del Bello's presentation about the rules around international relations in geo domain specifically, where operators want to stay in a particular slot, but there's no rules about how close they must stay to that prescribed longitudinal position. And a characterized pattern of life helps describe that behavior associated with station keeping at that position. So you might be having an average of that correct longitudinal position, but you're drifting quite a bit in longitudinal space, or perhaps you're drifting quite a bit in latitudinal space, getting nearby some of your neighbors perhaps in the meantime. So there's very interesting analysis for that particular application that we can do with this sort of work. And so I'm really optimistic about applying some of these techniques to that space in particular.
Yeah, I'm very excited to keep playing around with this idea of the using machine learning and doing these like clustering algorithms to see how these satellites get grouped. I would love to see if we can find trends in if these things are clustered by if there are trends for certain operators or certain buses or for certain propulsion types, stuff like that. And I'm really excited for the long-term implications of this, where potentially we could obviously identify this is what is nominal for this type of satellite, and therefore because we know what is nominal, we can detect abnormal behavior very early. But also you could say detect a new behavior or not detect, you could predict that you are going to see a new behavior from a satellite based on what you know about similar satellites and what they've done in the past. And I think that there's a lot of potential there. And I'm very excited that we are here to talk about this.
All right, well, that was excellent for all three of you. I'm pretty excited about the work that you're all doing. I'm biased a little bit there. So look, I would definitely like to welcome some questions from the audience, but first, I guess I'm gonna just kind of lead off with some questions. So starting with Ben, where do you really see this kind of algorithm shining? Where given all the stuff that you've already exposed it to, where do you see this algorithm really being able to shine in terms of how to kind of solve a lot of these SSA problems, given the variety of images that exist across the globe for people looking up in space?
So I think yesterday there was a discussion between I think semi-space and exoanalytics and the two theories of how we should go about optically observing objects. One of them being that we can rapidly task telescopes to look at different objects, and the other being that we can consistently watch the same object. And the difference between those two theories being what's the resource capabilities we have, and the trade-off between that and the confidence we have in where objects are in space. The more consistently we're able to keep custody of objects optically, the more confidence we have, the less uncertainty we have in where an object's positioned. Now, we do have lots of official network capacity that can be brought to bear in this problem, but we also have a wide body of, say, the amateur astronomers that, or other entities that are already looking at the sky, but don't necessarily have the experience of the algorithms for processing this and making meaningful such declination measurements that can be brought to bear in the problem. A methodology like this, which isn't necessarily intended for low SNR performance, but which can, with a very minimal amount of false positives, get you meaningful information from any kind of arbitrary data, can be used to sort of supplement our official capacities and make sure that we're improving or reducing the uncertainties in all of our positions, which we believe is critical. And also, if you're considering maybe an assisted lunar environment, as everyone who's very interested in, and you're using some kind of optical sensor that's on a telescope, if that sensor suddenly deteriorates, if the attitude behaviors or dynamics of the satellite rapidly change, can your algorithm still perform generally enough that you can make meaningful measurement data out of it? And obviously, for some applications, you'll have a traditional, say, convolutional neural network on board. But if there's issues with that, can you have some kind of backup system that can still reliably learn, regardless of whatever new noise models being introduced in the system, can it still make meaningful measurements that can be used to facilitate our space domain or space situational awareness?
Cool. Thank you very much. And then for the both of you, I guess, as somebody who's into statistical inference and that sort of thing, I'm very much enjoying the project that you folks are working on. I guess in some sense, we're interested in some phenomena, and in order to know something, you have to measure it, right? And so you basically, the measurements output data, structuring the data permit you to kind of get some models or hypotheses, and then these let you maybe predict, and that sort of kind of forms a cycle. I tend to favor abductive inference, which is kind of this data-driven kind of thing, and try not to come to the table with my own prejudices. But given what you've already seen in the unsupervised learning phase of this, if it's data-driven, then you're kind of beholden to how it was sampled, like all these things, right? So there's some of that. And then when it comes to the clustering, sometimes there's some knobs that you can kind of like finagle in the clustering itself to figure out like what kind of families is it, how many families is it generating in the clustering and all this other stuff. So can you speak to those sorts of sensitivities that you have already seen in the research that you've done so far?
Sure, and I think it might be appropriate to give a brief, contextualization of what we mean by unsupervised versus these supervised techniques. So when we say unsupervised machine learning, it means giving an algorithm a pile of data without any truth data. There's no answer that they're trying to find specifically for which that we can compare it to. It's not using any of our ideas for behavioral mode labels when it's deciding to sort all these behavioral modes into various clusters. And so Moriba was mentioning these clusters. How many clusters might this algorithm identify? Typically, as algorithm developers, we tell it how many clusters you should be trying to identify. But if you want to continue this unsupervised nature of this sort of work, where I really want it to do its best, find these patterns without my help, try running it on every number of possible clusters in a reasonable domain. So 2 clusters, just separating like behaviors into just 2 groups, all the way to high numbers, like something like 16 or 20 different behavioral modes. And you can measure how similar are those different behavioral modes in those different groups. And at what point is it getting like too many? Like you're finding differences that are too small to be forming these unique clusters. I think there's actually a lot of work left to be done on that particular work. But I think what's I'm enjoying doing is collaborating with people who are distinctly outside of the space domain. They don't have a background in astrodynamics. They're just asking for my help to produce a clean data set with which they can use cutting edge, state-of-the-art machine learning techniques, of which we can study and use, which is what happened in this study. But we aren't machine learning experts. Like, we're getting our PhDs, but not in machine learning. It's in astronautics, it's in domain-specific technical expertise. And so the real meat here, those questions about turning knobs and buttons are best answered in collaboration, where there's a real value in those experts using these algorithms not knowing the domain area expertise of this space community. And you know, vice versa. I can become a better researcher. We can become better researchers when we can focus on the space science and less on the machine learning. So I think there's some beautiful collaborations that are at play here, and we're starting up some of those in our lab right now. And so this is sort of some of the first work in that category, but we're particularly excited about where it can go in the future.
So I think that it's what you said, it's relevant to talk about the data that we were using. We were using TLEs, and this is relevant because there are certain periods of time, like there are, you know, up to a week, sometimes more than a week, where you don't have any new orbit information for these satellites. So if you're interpolating, you know, the longitude position between, you know, these epochs, they're not super accurate. So when we're looking at characterizing this pattern of life, you know, the history there, we're looking at very long periods of time, and we're avoiding the complication of having to detect individual maneuvers or, you know, the lack thereof. And that's great to simplify it, but then that also means that we are putting a lot of emphasis on the times when the satellite is drifting and segmenting those behaviors up into more behavioral modes than we would a segment of time where we can see that the satellite is station keeping, because we can't see on a fine enough time scale whether or not say the station keeping protocol changed within that period. We just know that it was station keeping. We don't know that it was station keeping in a consistent way. And I'm sure that has implications for the clustering algorithm, but I just know from the input data side, like that's a huge factor in that we have to consider.
Oh, yeah, love it. Anybody from the audience have any questions? How do you want me to just run the mic to people? Well, I won't run. I'll walk the mic to people. Sure.
Wow, really interesting. So, you know, a couple of things, differences between dead satellites in GEO versus the ones that are operating are you seeing any conjunction event type of things with your learning? And also then about anomalies such as, you know, I think it's China pulled using their, I think it was J21 pulling the GEO satellite out of orbit. You're seeing that, and then also something like I think it's the Intelsat 29E, where something happened to it and it was ejecting material, and it was going in and out of the orbit of the geostationary orbit. Are you seeing any of those kinds of things?
Yes. So the very first thing you said was about, you know, derelict versus active satellites. That's an example of a label we do not put into the machine learning algorithm. I wanted to tell me if it's detecting any control authority at all. I'm especially interested in cases in which it's detecting control authority when that satellite's actually labeled as a piece of debris or no longer an active payload. You mentioned Intelsat 29E. That's in a case of on-orbit anomaly when it was ejecting a bunch of mass and that was perturbing its orbit, you know, firing a thruster of some kind, but not the kind that it was designed to be doing. And so this sort of work can absolutely identify those behaviors as well. And I'd like to see it identify behaviors like that when we don't read the Space News article about it. Like, I'm familiar with that case because it's in the public domain. Intelsat is an actor in the domain that likes to talk about its on-orbit activities. They're frankly a leader in sharing their information about orbital planning. They'll tell you about their maneuvers that they're going to do. So that's not a good example of how the geosatellite operator international community works. They're an outlier. They're a great steward. So I want to find examples in which we can use machine learning to tell us those stories without relying on good stewardship from the space community, because we can find a lot of it, but we can't find it everywhere.
Cool. Other questions? All right. Want to go to the stage now?
Question for Thomas and Liz. Do you find that TLEs are sufficient to do the work you're doing, or would it be useful to have higher fidelity data like VCMs, and you can get access to those, or owner operator ephemeris, or just different, maybe better types of data?
Yeah, so do you like having crappy data or do you like having good data? Answer. Careful with how you answer that one.
I know. Yeah, we love having crappy data. No.
I was waiting for Beth to say something.
Thank you, sir. Yeah, obviously, you know, we can see behavior at smaller timescales like individual maneuvers if we have better data, but because we don't, and because a lot of people are, you know, they're working off of TLEs because that's what's available widely. We wanted to stick with the convention that worked for lower quality data as well. And this works. Like we were getting very good results for, you know, the nodes, at least, like for separating out, like, you know, the behavioral modes. We were getting a very high percentage of those detections from a really simple algorithm, even though the data was really bad, because it's actually fairly easy to filter out some forms of errors that you see in TLEs, like if you see cross tagging, or if you see just a really bad like orbit calculation, whatever. It's pretty simple to filter those out as long as they don't last more than 24 hours. So obviously, like the more frequently, you know, you have the orbit information, the better your results are going to be, but the results are still very usable and informative, even with the TLE data, even when it's pretty sparse.
Thank you. Thank you. And clearly Bass does not like TLEs.
He does not like TLEs.
All right. Who else has a question? All right.
You kind of alluded to this, but I'm interested in your thoughts on good uses of machine learning versus bad uses of machine learning in space. And particularly, it's interesting that you're all working tracking, but also in terms of onboard uses of machine learning. I've seen some interesting work, particularly from UT, about crater relative lunar nav using machine learning to do the like vision to detect craters. But yeah, what have you seen out there that you're more skeptical of in terms of machine learning?
Something that kind of gives me pause in this space is formulations that use machine learning for decision authority. So sort of abdicating your responsibility of having values, like how close can I get to my neighbor before it's a problem for me, or how high of a likelihood of collision is it a problem for me before I want to maneuver, but sort of throw away all those responsibilities and let a machine learning algorithm decide for you. I can just think a little bit into the future and imagine sort of the dark scenarios where things go really wrong, and a lot of good intention actors were investing in these sorts of solutions to avoid these sorts of problems, but they're not all avoided, especially as we have a more congested space domain, you know, using collision avoidance is a particular example. But instead, I want space operators to share their values publicly. I want people to take responsibility for how they believe that they're contributing to a more peaceful and sustainable space environment before we have an increased number of collisions. And when there are problems, I need actors to step up and take those responsibilities and change their behaviors as a result of it, not be able to blame a machine learning algorithm, especially one that maybe everyone uses. I'd instead like to see a more cooperative space environment than that.
Yeah, and talking about actors like this, it's important to know, to understand how the human is going to interact with some kind of machine learning algorithm in the kind of unsupervised manner that I presented. We're just detecting anomalies. We're saying, hey, this is not behaving like anything we're seeing. But there's no guarantee that's an actual object until you do further analysis on it. If you have some kind of decision authority that's being told to you by a computer, is it some procedure that you're going to trust or just blindly, or are you, what are the steps between what the computer outputs and what human action is going to be? I think that goes beyond how that's a discussion that's kind of beyond just how, the actual coding, the implementation of something. There are broad implications of how you work with machine intelligence to make meaningful decisions in space.
I guess the only thing I have to add is hello? Oh, there it goes. Okay. You asked about good and bad machine learning in this context. I think that the important thing is really to find a balance. You don't want to work too hard on like, oh, what can I get out of this with machine learning? It's like, that's not the point. You're trying to solve a problem. What is the most effective solution to that? Can you solve this analytically easily? If you can, then why spend all of this time and on figuring out how to apply the machine learning? It's like it's why overcomplicate it, and that's what you want to avoid. But there are a lot of contexts in which it is very difficult to look at something analytically, and machine learning can help in those cases and really simplify the problem. That's about all I have to add.
Cool. Any other questions from the audience? Yeah. Hold on a second, Joe.
I'm curious if any of your research went into the discovery of Cosmos 2499, if you remember that, on January 3rd. It was the Russian spy satellite that broke up, created a debris field at about 1,200 kilometers, 84 degrees, and it was the spy satellite that was moving. It was the one that was tracking all of the American spy satellites, and it had like a little Matryoshka satellite that would drop out of it. And then there was another Matryoshka satellite that dropped out of that. And it created a lot of anomalies that were detected. And I was wondering if you guys knew anything about that, or if that is something that came into your studies.
Was that this year, January of this year?
Yes.
Gotcha. So you guys may know about this, but the study that we did, like what's in our paper for Thomas and I, at least, the time span that we used didn't go past December 31st of 2021. So as far as the data that you can see in our paper, it won't be there, but you guys might be able to talk about that just from what you've seen.
It's also a low Earth orbiting satellite, so it wouldn't have been in the scope of our project. But it's a great story about how the way we do SSA doesn't always take into consideration some of the new anomalous behaviors we see in the domain. The catalogs we all rely on to make sure that you're looking at the right thing with optical data relies on us knowing what that satellite was. Like, it has to have a corresponding launch vehicle when it got onto orbit. That the satellite you were mentioning launched sub-satellites, which it reached orbit. Those new payload objects do not have the traditional storyline. I don't know if you could, do not have the traditional storyline of how they got to space. So there could be long periods with which we weren't tracking those objects, which means there's no data to feed into the machine learning algorithm. But could there be little clues in the data we do have? So in that story, can I switch?
Yeah.
I'm not sure if this one's going to be any better. But when you deploy a sub-satellite on orbit, that knocks your trajectory off kilter a tiny bit. And we were tracking that satellite that hosted those Matryoshka little satellites that pushed them off. And so you could detect small changes in that satellite's orbit. Could we see enough examples where we could start to characterize that behavior and begin to be able to detect sub-satellite deployments when we have no indication that they are going to happen? We do have some indication of some actors of better stewardship who share their plans in advance of deploying sub-satellites from their principal payload. There could be space situational awareness projects that partner with those operators to get a better idea of what that looks like in observation space to tell stories like this. But that example you gave wasn't included in the scope of our particular research.
Yeah, so the software that Benjamin's using, RMHF, that has the ability to do that. We've seen that. I've also saw that. I'm good.
Are you talking about for the orbit termination of the observations or the data collection of the observations?
Analysis and orbit determination, new things appear, like a maneuver appears or something happens. That's what I think the RMHF does a good job of understanding when something new happens.
I'm not here to advertise any of the work that I've done.
Yes, the CORMHF, that's a bit beyond the scope of what I'm working with, and I think a bit beyond the scope of almost beyond the scope of that problem itself. Yes, we need better orbit determination. We need orbit determination and filtering methods which can work on these bizarre events. Try to learn these sudden orbits, given if we have measurement data for them. One of the input considerations is that we need to feed something into CORMHF, and to do that, we do need observations on those data in the first place. So before we can even think about how we're going to make sure we can get orbit determination of these objects, how are we going to make sure we go about getting the information of these so we can process it? And to that end, we need, responsivity of the official network capacities. We need actors who have really good sensor networks that can rapidly change and focus on objects. But we are living in an environment now where everyone has a cell phone in their pocket and can't have a telescope in their backyard. And my interest is in how we can enable people to, use that data, get meaningful information out of it. Can we centralize this kind of data in such a way that maybe the Department of Commerce is interested in the future, and get these kind of data that are necessary to run these CORMHF processes so that we can make inferences and learn information about these important objects.
One of the questions that I have before I open it up to the audience again, that I was just kind of thinking about as people were asking questions is, especially with kind of this kind of, unsupervised machine learning kind of thing is, I'm just wondering, kind of a thought experiment, what if both of or all three of you simulated trajectories of objects just influenced by curvature of space-time, so all just gravitational only, and use that to feed into the system as kind of like a physics-informed way to do the machine learning. Say, hey, if these objects were only under the influence of gravitational sources, this is how the stuff would behave, kind of as a method of comparison to see the departure from that, and to what extent that might actually help you tease out other modes of operation that you previously didn't see.
I think that's a great description of like how machine learning was used for SSA papers from like 2015 to 2020. This is how a satellite would behave if it were just under a physics-based model, and you can do a bit better than just, Earth's gravity. You can apply the rest of the perturbative forces and propagators to say, like, if there was nothing cool going on with this satellite, how would it drift around? And then you take the observations and ask how much it deviates from that. That's the bread and butter for maneuver detection. But I think we're fortunate that we're a few years beyond that. And I want to tell richer stories than just when did this satellite maneuver, but to sort of tease out the broader storyline for why it might have been maneuvering, or what broader pattern does that maneuver fit into. A maneuver just in and of itself is normal place for the operational near Earth space environment. But some maneuvers make world news because of the impact they have on the international space community and because of how much we depend on space-enabled technologies, the rest of us on the ground. And so we want to build tools that tell broader stories than just that. So that is still the foundation of some of the questions we ask. Our algorithm uses maneuver detection, but we're fortunate to be a few steps beyond that, which is a really exciting place to be. I think we're doing this at the right time. I'd rather be here than 5 years ago.
Okay. Anybody else from the audience?
Thank you, everyone. My question I want to delve a little further into the good data, bad data, especially with AI models that can become a bit of a black box, and especially with generative adversarial networks and ways to try to spoof that, or like as the data quality gets lower and lower. I was curious if for all three of you, like if you were thinking about looking at what the PD-PFA curve or the ROC curve might look like as you try to get some definitive answers, whether you're labeling data, whether there's a maneuver or not, or whether there's an object there or not, what that could look like. So like how bad does a TLE has to get to be for yours to maybe fail? Or like how dim, what kind of knobs can you change? Like, has there been some sensitivity analysis into the PD-PFA world? Thank you.
With regards to the sensitivity analysis, to say our algorithm, the algorithm I was working on, we're getting to the point where we're going to be doing a large scale, like SNR responsivity study as part to finish up the dissertation work as this approach. The techniques we're developing on these kind of statistical inference techniques, they just look for anything that's anomalous in the data. And by anomalous, we're particularly meaning anomalous to the human visual system. Can you see something changing? And in methods like that, where you're working with perception, yes, there's going to be a weakness that can you conceal your object by making it look like something else that occurs. And the way around to tackle that would be to simply bring more information to the problem. You can't make a satellite behave exactly like a dead pixel because it has dynamics that are unique. It's not going to behave like the stars because it's not infinite AU out. And I think that's that's something that is important for, I think, the broader body of machine learning. That if something's going to, oppositionally try to conceal behavior, there are always ways to attack that. You have to know the shortcomings of where you are and then how to evolve beyond that. It's always going to be a cat and mouse problem where you're always trying to advance the amount of information you can bring to the problem to discover these patterns. And I believe you're probably going to say something similar.
Well, I feel like you were sort of touching on the least cool part of this very cool. It's a really important thing, data cleaning. Like whose job it is to like figure out if this data is any good. Like we have this shared understanding that TLEs aren't any good, but I also need to make sure my work is reproducible. I want people who are not from the US, who don't have access to some of these commercial SSA providers, or aren't at MIT or UT and have all these partners who can give us this high fidelity data. I want them to be in on this conversation too. And so we have to pay a lot of attention to making the tools we have available, TLEs in this case, good enough for the analysis that we're doing. And I think that we are the only people that are going to do that. Like it'll take the SSA side expertise to clean up TLEs and answer questions on how bad is too bad. Then the ML experts who are designing novel new algorithms because they aren't familiar enough with this. But I kind of fear that we all don't think it's cool enough to be working on that. And so you sometimes see papers dive right into this sort of analysis because that's the fun part without answering those really important questions. I think I'm guilty of that. And I think a lot of people in the research community are too. Or spending more time understanding how TLEs are created. We've had some really fruitful conversations with some of our collaborators on how TLEs have been created over time. We use a long study period from 2010 to 2021. TLE generation practices have changed from 2010 to 2021. but you don't find the methodology page on spacetrack.org. But it's not there.
Booyah. With that said, we're kind of up, so if you had one quick thing to say, a takeaway that you want for people to end this panel with, what would it be and what would start with?
I guess just, I would love for people to start, just talking about this. Like, there are so few papers out there about pattern of life and, analyzing this at like a large scale, like across the geo population or, across the LEO population, whatever. It's mostly focusing on, very specific groups of satellites. And I would love to see this done at a much larger scale, so that we can see trends across that.
I really want to see that collaboration between ML experts and SSA experts, some nice hand holding between our operational expectations for environments and just what the data shows when you are blind of all of the heritage history of the domain and our personal experiences leading some of these areas.
Probably more data isn't always better, but diverse data is always better. And if you're looking at patterns of life, if you're trying to make detections, you don't necessarily need the same camera to give you a bunch of observations. You need more diverse data sets, and from those you can have machine learning algorithms learn more interesting behaviors. You can get more confidences. And so not just the ML techniques are important, but how you're feeding into the ML techniques is important.
I want to thank all three of you. I want to welcome the audience to thank our panelists and hope you all enjoyed this panel. Thank you very much.